Well, we're going to continue in section 3.1, which is continuity of a function at a given point by doing an example. And it's going to use the definition, of course, and we're going to use, therefore, the delta epsilon method for proving this. We've got a function f from the reals into the reals, and it's defined as this. It's simply a polynomial. And you probably all remember already that polynomials are everywhere continuous. But we're going to prove, using a delta epsilon proof, that f is continuous at this point in particular, x naught equals 2. Now, in working this problem out, I discovered I needed to do a lot of algebra, so I created a lemma, and you'll just have to trust me as to how it's going to help us. But you would have come up with the same thing after trying to do this proof. So the lemma that's going to make our lives a little bit easier, I'm going to have to write small here. So before I actually prove what I'm trying to prove, I'm going to write a lemma that I'll use in the proof. And the lemma says that if x minus 2 in absolute values is less than 1, then x plus 2.2 is less than 5.2. And I know that sounds very obscure, but you'll see why I want to prove this. So if x minus 2 in absolute values is less than 1, can anybody explain what that statement means kind of graphically or geometrically speaking if we were drawing pictures? Maybe I'll draw the picture here and then erase it in just a second. What does this mean? Using the word distance. When you take the difference of two numbers and put them in absolute values, that's the distance between the two numbers, right? So this says if the distance between x and 2 is less than 1, then what? Negative, right? This needs to be, for it to be distance, it needs to be a negative sign. So it would be, that's the same as minus negative 2.2. So this would be, if the distance between x and 2 is less than 1, then the distance between x and negative 2.2 is less than 5.2. And that's really easy to see. This is not part of the proof. I'm just going to show it kind of graphically speaking. Okay, the two numbers we're looking at are negative 2.2 and a positive 2. So let me see, that would be like negative 1, 0, or 1, something like that. Let's just say that's negative 2.2. Well, if the distance between x and 2 is less than 1, that means you're in this region, right? Only these numbers are a distance less than 2 from, distance less than 1 from the number 2. Well, if I want the distance between x and negative 2 to be less than 5.2, if this is true, okay, so centered here, if I go out a distance of 5.2, well, where does that put me? That puts me, if I add 5.2 to here, it takes me out to 3. If I subtract 5.2, I don't care about that. It would take me way out here. So if I'm this close, if I'm in this region, the farthest that I could possibly be away from negative 2.2 is if I were almost right at 3. And that would be less than 5.2. So graphically, it's simple, but this will be a good practice for using absolute values if you're not familiar with or comfortable with absolute values. Well, let's prove this lemma. All right, so we assume this is true to show that this is true. So maybe I'll put proof here. Proof of the lemma. X minus 2 less than 1 implies what? What is the definition of this absolute value inequality. What's another way of writing it without the absolute values?
X minus 2x plus 2 and 1 in between.
Zeros. Zero is less than x. No.
Well, let me start you off. X minus 2 is between what?
It's between negative 2.
1 and negative 1.
And negative 1.
That's the, I mean, this is just the definition of absolute value, right? All of the numbers in between negative 1 and 1 have absolute value less than 1. So that's the definition. Actually, I can make this a double arrow. This is essentially the definition. They are equivalent statements. And now we just need to work toward what I'm wanting to get to. So that implies I need this to be in the middle. So I am going to add, what, 4.2 to get x plus 2.2 plus 4.2 plus 4.2. Add that to all three of those sections, and we get x plus 2.2 in the middle. And I get 5.2 on the right, and I get 3.2 on the left. And actually, that's another if and only if. These are equivalent, these all three are equivalent statements. Any questions so far? Well, the next thing I'm going to do is not going to be an if and only if, but if this is true, if x plus 2.2 is between these two numbers, then what do you think I'm going to put over here? Any idea? Negative 5.2. If it's between 3.2 and 5.2, then certainly it's also between this, the bigger interval here, right? And I did it this way because now I can jump right to this definition. That exactly means that x plus 2.2 in absolute values is less than 5.2. That's the proof of the lemma. Even though we could kind of see it in that picture, I thought it was worth going through this proof. And yes, this is the only implication. These are not equivalent statements. But if this one is true, then this one is also true. Okay, so any questions on that? Because I'm going to have to erase it before I write the rest of the proof. I'm going to at least erase the proof. Or maybe I can leave the lemma up there. No questions? All right. Okay, if I erase the proof. Right. So I'll just leave this statement of that lemma up there. And now let's do the proof of the original statement now. Well, I want to prove that f is continuous at x naught plus 2, so I need to use the definition, which means I need an epsilon greater than 0. And you will see why I am picking the value of delta. I'm going to let delta be the minimum of 1 and epsilon over 26. Now you'll see exactly why. You would have come up with this value just as well. If you were trying to prove it, you would have realized that if you just said let delta equal epsilon, it would fail. But you could easily see that there's a way to fix it, to correct it. All right, well that means then, thus, what do we need to check for continuity? If x minus 2 is less than that delta, then, and now we need to show that f of x minus f of x naught, which is f of 2, is less than epsilon, just using the definition of continuity.
Where did epsilon over 26 come from?
That's what I was just saying. I've already worked the problem out, and I discovered that was necessary, not the only possible value. Any value smaller than that would work as well. But you'll see where it came from in just about 2 minutes. Okay, so we've got this, which implies what I want is f of x minus f of x naught, which is f of 2. And somehow with some algebra, I need to prove that this is less than epsilon, and then we'll be done. Well, let's write out what that's equal to. F of x is this, 5x squared plus 2x minus 3. And I need to subtract f of 2. All right, scratch paper. F of 2 is going to be 5 times 2 squared plus 2 times 2 minus 3. So we get to 420. We get plus 4 minus 3. So f of 2 is 21. Okay, this right here, make sure I did that correctly. It is 21. That's 21. So minus 21. That's just using algebra. That's not using any theorem or anything. And now I'll go ahead and simplify that. 5x squared plus 2x minus 24. Okay, now this is going to take you back to pre-calculus, probably. I'm going to write a little scratch work here, or maybe over here. That way maybe I can leave it up on the board. I need to factor that. And I need to factor it in a way where I have no way of limiting this. I don't know how to limit this. But if I can factor it and find an x minus 2, I'm on my way. All right, so
Define it x minus 2.
in the factoring of that. So if I take this polynomial and divide it by x minus 2, I want to get this equals x minus 2 times something. All right, anybody remember how to do synthetic division? You could do long division if you want to, but I know because I've worked it out that x minus 2 goes evenly into this. So you don't have to memorize this if you don't know synthetic division, but I'm going to go ahead and do it as if you know it. X minus this number, you put this number in the cup, they call it sometimes. And then you put all the coefficients, 5, 2, negative 24, like that. So does this look familiar to 2 or 3 of you? Okay, well, you bring the 5 down, you just bring that number down, and then you just do this repetitive process. You take the 2 times this number and you write it right there. And you add the next column, and you repeat that over and over. So 2 times 5 is 10. Add this column to get a 12. 2 times 12 is 24. And that becomes a 0. That's your remainder. So since it's 0, it means x minus 2 went into this polynomial evenly with no remainder. And this also tells us what the other factor is. So I can say by factoring that that's equal to x minus 2. Now maybe I'll write it like this. X minus 2 times what? X squared plus 12. Sorry, 5x plus 12. Remember that? You would have got the same result if you did long division. Or if you were really good at factoring in your head, or use some of those other pre-calculus techniques, we would have come up with the same result. What's that? Yep. Okay, so maybe I'm going to write this like some absolute values. By absolute value arithmetic, I'm going to factor the 5 out of this. And if I factor the 5 out of this, what do I get? X plus what? 12 over 5, 2.2, which is why we did that lemma earlier. Okay, well, what does that tell us? That is less than, I want it to be less than epsilon. So that's less than 5. X minus 2 in absolute values is less than delta. Delta. And I know that x plus 2.2 is less than, let's see, since I know x minus 2 is less than 1, because I made sure delta was was at most 1. Since this is true, x plus 2.2 is less than 5.2. And that is equal to 26 delta. And 26 delta is less than epsilon. I'll say less than or equal to epsilon. And that's the end of the proof. So again, that's the kind of problem where you had to just try something and fail, and then realize, by failing, if you would have just said choose delta to be epsilon, you would have realized that that wouldn't have worked.
So, what if delta was like equal to epsilon over 26? Did you do that? Or did it have to be the minimum or something?
Well, I needed to make it less than 1. If you chose an epsilon of 30,
Yeah.
then this would be bigger than 1. 30 is a big number. You probably wouldn't, but you could. I needed to make sure in order for this limit to hold true, I needed it to be less than 1.
So epsilon does not need to be less than 1 in this case, does it?
Epsilon does not need to be. Just delta.
Just delta. Okay.
So, and you can make, all you need to do is show that there exists a delta, and we're just making it a small number that's less than or equal to both of those numbers. So any questions on this delta epsilon proof? Yeah, it was more algebra intensive than most.